Welcome to an extra special mathology video. Why extra special? 3 extras. Well, first extra, it's the 100th official mathology video. There, the thumbnails for the first 99 videos. It's been quite a journey. Second extra, it's my first crossover episode. For the first time, I'm collaborating with another channel. Mathematician and 3D printing artist Henry Segerman just published a video that complements this mathology video. I'll have more to say about Henry and his wonderful claw contraption down there in the last part of this video. Now, most importantly, third extra, in today's video we'll make a little bit of mathematical history. I'll tell you about a couple of brand new game-changing discoveries about the good old sphere that so far only a handful of mathematicians know about. Yep, you've been invited to opening night, a mathematical premiere. Have a look at this. You're all familiar with this kind of baggage carousel, right? Really ingenious how it flows around corners, don't you think? What makes this work is the crescent moon-shaped pieces the belt consists of have circular sides that can seamlessly rotate one against another. Let's steal this idea. First, create a circle-shaped conveyor belt. And then have this conveyor belt perform a figure-8 dance like this. Very pretty, isn't it? On close inspection, what is happening here is that the circle gets turned inside out. Have another look. Right? Points that originally are close to the center of the circle end up on the outside of the new circle and vice versa. Very nice, but so what? Is there any more to this? Well, let's put a hemisphere on top of this circle. Wow, that animation really turned out very nice, don't you think? Okay, now in the same way as before, let's turn the hemisphere inside out. Okay, what on earth is that? What's that inside out shape? Well, on close inspection, it turns out to be approximately a cylinder with a cone carved out from the top. In fact, by using thinner and thinner moons, the new shape will get arbitrarily close to a true cylinder minus a true cone. There, thinner moons, even thinner, infinitely thin. But turning the hemisphere inside out like this doesn't affect the volume. This means that the volume of the hemisphere is equal to that of the cylinder minus the cone. Now, finding the volume of the sphere, that's a tricky one, right? One of Archimedes' great achievements. But with our baggage carousel trick, all we have to do to find this tricky volume is to subtract the volume of the cone from the volume of the cylinder and then double. And that's all easy. The volume of the cylinder is just base times height, and with the height being the same as the radius r of the sphere, the volume of the cylinder pans out to be pi r cubed. And pointy things always have 1/3 volume of cylinder things, also pretty easy, so we subtract 1/3 pi r cubed. All right. Then doubling to go from the hemisphere to the sphere gives the volume formula of the sphere. Ta-da! 4/3 pi r cubed. From baggage carousel to the tricky volume formula of the sphere, pretty much at a glance. How great is that? Definitely made my day when a couple of weeks ago my colleague Andrew Caput, a mathematician at the University of Newcastle here in Australia, pitched this and a couple of other ingenious sphere-related ideas to me. And here we are, a mathology video featuring Andrew's ideas. What I'll do next is flesh out and milk this baggage carousel idea for all it's worth. After that, it's on to Archimedes' claw, Andrew's second great idea and possibly the climax of this video. That's also where 3D printing master Henry Segerman makes his appearance. Anyway, prepare for a life-changing experience as far as all the spheres in your life are concerned. Enjoy! The inverted hemisphere is a cylinder minus a cone. Really? Well, the animation that I just showed you was very convincing. But of course, to be absolutely sure that this really works, we need to conduct a proper mathematical check that the shape on the right is really a cylinder minus a cone, with both shapes of just the right dimensions. Okay, is there anything that can go wrong with the cylinder? Well, let's have another look at how exactly the hemisphere turns inside out. There, the orange arrow points at the highest point of the hemisphere, and the green arrow marks the point around which we are figure eighting as we turn the hemisphere inside out. Focus on what happens around those two special points. Ready? Go! Okay, pretty obvious. The mantle of the inside out shape is that of a cylinder of the same radius and height as the hemisphere, and the lowest point of the inside out shape is right in the middle. All convinced? Great! So nothing can go wrong in terms of the cylinder. But what about the carved out bit? Is that really a cone? Basically, what I'm worried about here is that those mantle lines that appear to be straight, as in a cone, may actually be a tiny little bit curved. I'll just quickly sketch one way of proving that looks are not deceiving. The keen among you can then fill in the details in the comments. Okay, for easier tracking of distances, let's also display what the vertical cross-sections of our shapes appear to be. There. All right. Cut everything inside with a horizontal plane at height h. Then it's clear that the red cross-section on the left will be a circle and that the red cross-section on the right will be a ring. And it's also easy to see that the circle and the ring have exactly the same area. Is that clear? Right? During the inside-out dance, the circle cross-section on the left continuously turns into the ring cross-section on the right. And so the circle and the ring must have the same area. Now, using this equality, you can then calculate the inner radius of the ring. For this, hire a couple of middle school kids and put them to work. All they have to do is write down the formulas for the areas of the red circle and the red ring and then solve for the inner radius. They've done stuff like this in school a million times. Piece of cake. Eventually, they'll report back to you that the inner radius exactly equals the height h at which we cut. That's a linear relationship, and that means that those mantle lines are really straight. They're straight. And so the missing part in the middle is really, truly a cone. All good? Everybody happy? Great. Proof complete. As I said, just a sketch, and as long as you got the gist of what's going on here, that's good enough to be able to appreciate what I'm about to say. Okay, while Andrew's method of turning the hemisphere into the cylinder minus cone shape on the right is definitely brand new and brilliant, the basic idea is not new. 400 years ago, the mathematician Bonaventura Cavalieri was the first to realize that the cylinder minus cone configuration can be used to derive the volume formula of the sphere. Of course, like Archimedes, Cavalieri was not familiar with air travel and fancy baggage carousels, and so it's not surprising that his line of reasoning was a bit different from ours. In particular, Cavalieri doesn't motivate why he's comparing the two shapes over there and starts by showing from scratch the crucial property of the two shapes that the baggage carousel gives us for free. What he does is, he starts by showing that the circle and ring cross-sections of the two shapes have the same area no matter the height at which we cut. Right? We got that equality for free. He then finishes his proof using Cavalieri's principle, an ingenious idea named after him. Cavalieri argues that because there are cuts of equal areas at all heights, the two shapes must also have the same volume. Equal area cuts at all heights implies same volume. Makes sense. Cavalieri, considering those two shapes, was probably inspired by Archimedes, the original discoverer of the volume and area formulas of the sphere. I won't go into the details of Archimedes' proof, but let me at least give you a glimpse of his setup. There's also a sphere-cylinder-cone combo at play, but it's all a bit more complicated. If you're interested in more details about Archimedes' proof, there's a link in the description of this video to an old Maths Masters article by Marty and me in which we rave about this proof. Anyway, I think Andrew's new way of naturally turning the hemisphere into the cylinder minus the cone shape is an important upgrade of Cavalieri's discovery, which in turn was an upgrade of Archimedes' original proof. As I said, we are really making mathematical history today. Mathematical history that's been in the making for thousands of years. You saw it first in Mathologer. Pretty amazing, isn't it? Okay, before I move on to the next main topic, let me just mention one more beautiful insight that arises from Andrew's dance. Here we go. If we replace the hemisphere by a paraboloid, something extra special happens. What's a paraboloid? Well, that's a solid we get when we spin the graph of our good old friend y is equal to x squared around the y-axis. Well, to be nitpicky, that's not the whole paraboloid, but rather part of the paraboloid below a certain height and turned upside down. Whatever. Let's call this bit a paraboloid anyway. Now here is what the corresponding inside-out shape looks like. And here's the amazing bit. The inside-out shape turns out to be the surrounding cylinder minus the same paraboloid. Challenge for you and your army of middle school minions. Work out the details in the comments. Anyway, how great is that? And so what do we do next? Well, solve for the volume of the paraboloid, of course. There, solve, 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 solve. The volume of a paraboloid is equal to half the volume of the surrounding cylinder. Archimedes was also the first to discover this surprising formula. Did I ever mention that Archimedes is my #1 mathematical hero, with Euler being a close second? Actually, at this point, I just have to tell you about yet another one of Archimedes' ingenious insights. So much great stuff to point out here. For this insight, let's spool back to this earlier slide. The volume of the hemisphere is 2/3 pi r cubed. Okay. Now, pi r cubed by itself, what's that? Well, pi r cubed, remember we had this before, that's just the volume of the cylinder. Let's shuffle this formula around a bit, there and there. Okay, but now it's also clear that the hemisphere fits snugly inside the cylinder. And so what our identity says is that the ratio of the volume of the surrounding cylinder to the volume of the hemisphere is equal to 3:2. And of course, the same is true if we double everything inside. The ratio of the volume of the surrounding cylinder to the volume of the sphere is 3:2. How nice is that? Archimedes was so impressed by the simple relationship that he had a version of the cylinder-sphere diagram over there engraved in his tombstone. In fact, he noticed something else which makes all this doubly amazing. It turns out that the ratio of the surface area of the cylinder and the surface area of the sphere is also 3:2. So both the volumes and surface areas are in the ratio of 3:2. Did you know that? Fantastic. Anyway, this is our cue to now have a closer look at the surface area of the sphere. Okay, so we've mastered the volume formula of the sphere. What about the surface area? Let me just go for it and power through a simple and beautiful argument that gets us there without breaking a sweat. I'll start with a quick warm-up exercise that quite a few of you will already be familiar with. Let's have a look at a disk of radius r. We can think of this disk as being made up of infinitely many concentric circles. Here I've just highlighted a few of these circles. Let's cut the circles open at the top and then straighten them out. There, straighten, 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 straight. In this way, the disk unfolds into a triangle of height r. What's its base? Well, the circumference of the disk, of course. That's where the base comes from, right? And so the area of the circle is equal to the area of the triangle, which is 1/2 base times height, 1/2 circumference times r. Nice argument, don't you think? And what's extra nice is that in this way we've discovered a simple relationship between the area and the circumference of the circle without any pi inside. Now, of course, once we know this relationship, then also knowing the formula for either one of these quantities immediately gives us the other formula. For example, let's say we know the formula for the circumference 2 pi r, then plugging in we immediately get the area formula. There. Bit of algebra autopilot, simplify, simplify. Hands up! Who's seen this proof before? As expected, quite a few of you. Okay. The nested circles that we started with are reminiscent of an onion. And the argument that I just showed you is often called the onion proof. Dad joke alert. Did that proof make you want to cry? Yes or no? That's a bad one, but I couldn't resist. Now, what even those of you in the know may not know is that the same argument also works in 3D. Let me show you. Replace the layered disk by a layered ball. There, layered. Like an onion. Okay, that's it for onions, I promise. Then we can unfold all the layers into disks of the same area like this. Unfold, unfold, unfold. There we go. All right. And so the ball unfolds into a circular cone of height r. And of course, the base area is equal to the surface area of the ball. There. And so the volume of the ball is equal to the volume of the cone, 1/3 base area times height, and so 1/3 surface area times r. As in 2D, in this 3D onion proof, pi is nowhere to be seen. Cute, huh? And now, since we already know the volume formula of the sphere, we can figure out the formula for the surface area. There, a bit of algebra autopilot again. Simplify, simplify. Okay, ta-da again. And so at this point, we've proved both the volume and area formulas of the sphere. And now you also know why these formulas look so similar. 4/3 at the top and 4 at the bottom. That wasn't hard, was it? And Archimedes definitely looks pretty happy over there and has probably pushed the like and subscribe buttons by now. What about you? Actually, although what I just showed you was a pretty quick way to derive the area formula from the volume formula, there is an even quicker way. If you are a calculus demon, at some point of your career, you may have noticed that the surface area formula is just a derivative of the volume formula. Wait, what? Yes, quick check. The derivative of r cubed is 3r squared. Okay, simplify. There. The derivative of the volume formula is the area formula. Magic. You may think that this is a coincidence until you try the same for the circle, the 2D counterpart of our 3D sphere. Turns out the derivative of the area formula for the circle is the formula for the circumference. There. Pi r squared and 2 pi r, the formulas for the circle, and of course the derivative of pi r squared is indeed 2 pi r. Magic again. Really easy challenge for the calculus demons among you, even those of you who are still in high school. Can you provide an onion-powered calculus explanation for this derivative magic? If so, dazzle the rest of us by leaving your thoughts in the comments. Go on, give it a try. Otherwise, I'll also link to a brief explanation in the description of this video. Another challenge. Check that Archimedes 3:2 really also works for the surface areas of the cylinder and the sphere. Okay, back to our formulas. Which of the two formulas do you like better from a purely aesthetic point of view? I think pretty much everybody would go for the area formula, 4 pi r squared. No fraction inside, and so cleaner, prettier, more beautiful. All right, we're now ready for the second main attraction of this video. Andrew's ingenious new way of seeing at a glance why the area formula is what it is. Does the pi r squared in this formula ring a bell? Of course, pi r squared is just the area formula for a circle of radius r, like for example an equatorial circle cross-section of the sphere or its shadow. In other words, the surface area of the sphere is exactly 4 times the area of its shadow circle. A couple of years ago, 3 Blue 1 Brown set out to find a nice visual way of seeing at a glance why this is true. Today, I'll show you the ultimate one-glance way of understanding this relationship from scratch, something that I think is even nicer than what was shown in that 3 Blue 1 Brown video. This is the result of another one of Andrew's brainstorms. Andrew started by observing that there is a better way to write the area formula if you're hunting for a one-glance proof. There, pi times 4r squared. Since 4 is also 2 squared, we can pull out the 2's in the exponents. And what that means is that the area of the sphere is equal to the area of the circle of double the radius. And now that this is true can indeed be seen at a glance using an ingeniously weird unfolding of the sphere surface into this larger circle. Here's what we do. We start with the infinitely many meridians of longitude. Here are a few of them. Okay, so every meridian is a semicircle that joins the north and south poles of the sphere. And except for the two poles, every point on the sphere is contained in exactly one of these meridians. Let's focus on one of the meridians, this one here. There's a radius of the pink circle right below this meridian. There it is. We now swivel the meridian 90 degrees clockwise around this radius. The swivel fits perfectly. Let's do the same with all the other infinitely many meridians. I'll just illustrate with the few meridians highlighted over there. Okay, after we folded down all the meridians, they completely fill the pink circle. To really get a feel for this unfolding, let's turn the sphere into an Earth globe. Ready? There, unfold. Each individual meridian folds down nicely. The meridians all snugly fit together and fill the big circle when folded down, without overlapping. Wonderful. So there, that's how Andrew's unfolding morphs the surface area of the sphere into the circle of twice the radius. All clear? Now Andrew's simple transformation happens to have an incredible magical property. Obviously, the transformation distorts the sphere like crazy, but there's one thing it doesn't distort: area. To use the jargon, Andrew's magical transformation turns out to be area preserving. This means that any region on the sphere will be transformed into a distorted region somewhere on the large circle of exactly the same area. For example, have a look at Australia on the globe. Then the area of Australia on the globe is exactly the same as the area of its image on the circle. Amazing, isn't it? And the same is true for any other region on the sphere and its image on the circle. In particular, this means that the area of the entire sphere is the same as the area of the circle. Ta-da! Proof complete. Well, not so fast. Definitely everything I said is true, and you know me, right? Would I lie to you? But of course, that's not the way things work here in Mathologer land. I have to at least sketch a proof. Now, first, to see how things could potentially go wrong, let's do the same sort of unfolding for a cylinder of height h. There, the cylinder is of height h. Now fold down all the mantle lines. There. This means that the unfolded cylinder mantle is this ring. And so, are the surface areas of the ring and cylinder mantle the same? What do you think? The answer is definitely not always. That's easy to see. Just think about it. Keeping the height of the cylinder fixed, we can make its area as close to zero as we wish by making the cylinder thinner and thinner. On the other hand, the ring area will never get smaller than the area of the circle whose radius is equal to the height of the cylinder. There. Basically, that's the circle of radius h. And so the two areas are definitely not the same. So why is the sphere so magical? Why does unfolding the sphere not distort the area? And can it be easily seen why this is the case? Well, remember Henry's claw contraption, which I showed you at the very beginning? Henry's gizmo is a 3D printed version of Archimedes' claw, another one of Andrew's ingenious inventions. Have a look. So here we have the whole surface of the sphere covered by special 3D crescent moons that are thickened up versions of the meridians from before. Let's fold down those 3D moons together with the meridians. As we fold, the moons keep touching without a gap and end up forming a thickened up version of our target disk. There again, no gaps, completely smooth, magic. And then, as we increase the number of moons, we're getting closer and closer to the real thing. So look, there and there and, well, there you have it, the surface of the sphere rigidly turning into the disk without any distortion. Ta-da! Now the proof's complete, right? Well, again, not so fast. Take my word for it. We're getting closer to the true explanation of this area preserving property. However, I'm fairly sure that what most of you are thinking here is that because the moons approximate the sphere and the circle better and better, the total surface area of the bits of the moons facing out will get closer and closer to the surface area of the sphere and the circle, which then somehow completes the proof. Right, seems at least plausible. However, that's not quite it. Have a close look at the moons. Arranged in sphere mode and circle mode, we are really looking at the moons from completely different perspectives. And so, although there are never any gaps between the moons as they move, how can we be sure that these different perspectives really translate into the same surface areas? Not obvious, right? Okay, let's have a closer look at where those moons actually come from and what is happening here in terms of areas. There, the sphere and the circle before and after folding down the meridians. The meridians divide the blue and pink into the same number of regions. And so, to show that the blue and the pink have the same area, we just have to show that a blue region has the same area as a pink region. Okay, so to be able to compare these two regions, let's fold down the blue region and align it with the pink one, like this. Now watch this. There's a little miracle at work. The traveling sphere always exactly touches the sides of the blue and pink regions. Okay, very cute, but so what? Well, for once, you now know where those 3D moons come from, right? There, one 3D moon served. Now let's get rid of the sphere and let's focus on the growing moon surface by itself. There it comes. Very nice. What you're looking at here is a circular cross-section of the traveling sphere. Furthermore, the pink and blue cross-sections of our two regions are both roughly diameters of the circle and so approximately of equal length. And the same is true all along the 3D moon. And now we're in a familiar situation where two shapes are the same cross-section by cross-section at corresponding levels. Remember Cavalieri? And as usual, we can conclude that we're dealing with surfaces of the same area. Well, since corresponding cross-sections are not exactly the same in the case of large moons, the surface areas of the two regions will not be exactly the same. However, as we push the number of moons to infinity, in the limit, we'll have equality, which is what we've been chasing. Okay, so the sphere and the large circle have the same area. Very, very pretty. Also, looking a little closer, we can refine our argument to prove that Andrew's transformation is always area preserving, that any country on the sphere transforms to a country on the circle of exactly the same area. To make this argument rigorous still requires quite a bit of detailed fiddling, but what you see in front of you really nicely captures the core of the proof. And that's definitely good enough for now. Okay, and that's pretty much it. But before I sign off for today, I wanted to thank Andrew for inspiring me to make this video and for creating most of the fancy animations in this video. And this is a Mathologer command. You must check out Andrew's playlist of relevant animations linked in from the comments. Also, thank you to Henry for creating the 3D printed version of the claw. Another command. Make sure to head over to Henry's channel for his video about the claw plus free 3D printing files. Then you can print your own copy of Archimedes' claw. As usual, there will be more thank yous at the very end of this video. Now, I should mention that in terms of Archimedes' claw, I've really just touched upon a few of the secrets it holds. There's definitely enough material for a part 2. Just to whet your appetite, there is the beautiful explanation and important implications of the fact that as the claw opens, all its moons will always touch without leaving any gaps. Then there is the important connection to Heinrich Lambert's famous area-preserving map of the sphere. Remember polymath Heinrich Lambert? We keep running into him. He was the first to prove that pi is an irrational number. He was one of the inventors of the hyperbolic trig functions. Then there are all of Lambert's amazing maps and so on. Anyway, Archimedes' claw, there's a lot more to be said and to be discovered, but let's call it a day. I'll finish with one more of Andrew's stunning animations, illustrating a completely different moon-powered way to turn the surface of the sphere into the circle. Enjoy!